In this video, we'll talk about exponent function, that is m power n. So raising m for n times, that is multiplying m for n times. So for this problem, we will try to define a recursive function. For that, first of all, I will explain what the problem is. See, suppose I have to find out 2 power 5. So this means 2 into 2 multiplied by 2, and this is multiplied by itself for 5 times. So it means m power n means m should be multiplied for n times, m should be multiplied for n times. Now this, if I write it as a power function, that is power m comma n, then it means m into m into m, that goes on to n minus 1 times into 1 more time. This will continue for n minus 1 times and 1 more time. For example, 2 power 5, see this is 4 times, and 1 more time. So same way, m power n means m should be multiplied for n minus 1 times, then again multiplied by 1 more time. So it becomes total n times. Now this I can define it recursively. I can say power of mn is power of m comma n minus 1 times into m. So yes, this can be defined as a recurrence relation, power of m comma n minus 1 into m when n is greater than 0. When n has become 0, then when n is equals to 0, as it is a product, so it should return 1. So minimum value is 1. So that's it. So for this mathematical definition, I can write a recursive function using C or C++. So let me write a function here, integer power int m comma int n. If n is equals to 0, return 1. Otherwise, return power of m comma n minus 1. So that's all. It is just a 2-3 line functions. It's a simple function. So this is converted into a recursive function. I will take one example and show you how it works. Let us trace this one for power of 2 raised to 9. So 2 raised to 9, m value is 2 and n value is 9. So 9, that is not equal to 0. So it should perform this operation. That is power of 2 comma n minus 1, that is 9 minus 1, that is 8. So I will rewrite it as 8 multiplied by m. So what is m? This is 2. So that's it. Continue. Now this call has to be finished, then only multiplication will be done. So what this call is? Power of 2 comma, as this is 8, it is not 0. So every time this has to be done. So this will become 7 multiplied by 2. Then again power of 2 comma 6 multiplied by 2. And power of 2 comma 5 multiplied by 2. Power of 2 comma 4 multiplied by 2. I'll finish this. So that's all. I have made all the calls, and the last call is 2 comma 0. So 2 comma 0, when n is 0, it returns 1. So this will be 1 multiplied by 2. So result is 2, and it returns here and multiplied by 2. Again it is 2 square. 2 square returns here. So this is multiplied by 2. So this becomes 2 cube, and so on. So I don't have to work out on this one. So you can see that 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 times 2 is multiplied. So the result is 2 power 9. So for value of n as 9, it has made a total 10 calls. 9 to 0, total 10 calls. So n plus 1 calls. So now you know how much time it is taking and how much memory space it is consuming. As there are 9 plus 1 calls, so it is n plus 1 and it is order of n, time is order of n. And what is the size of the stack? That is also order of n. Because the number of activation records created inside the stack are dependent on the number of calls, that is n plus 1 calls. Now one more thing we should analyze here, we should observe here. Total how many multiplications it is performing. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So total 9 multiplications are performed. So is it possible to compute this one with less number of multiplications? Let us check, is it possible to do that? See, here if suppose it is 2 power 8. So 2 power 8 can be written as 2 power 2 and power 4. So this is 2 into 2 power 4. So it means if I perform one multiplication on the same value, then power will reduce by half. Power will reduce by half. And suppose it is 2 power 9, then this can be written as 2 into 2 square power 4. So because it is odd, we can't directly make it half. So first 1, 2 I have taken it out, and this I made it as 2 power 8 again. So I can make it half. So if the power is even, then I can directly half it out. So if the power is even number, then I can directly take half of the power, and if the number is odd, then I can take one multiplication extra and then I can take half of the power. So if I multiply the number directly, then the power is getting reduced by half. So with this observation, we can write a power function faster than this one. So let us rewrite that power function. Here I will write on power function, integer, I'll give the same name, power, though it's a new version, m and n. First of all, if n is equals to 0, then return 1. Now next check if n is even. If n is mod 2, if it is equal to 0. If n mod 2 is equals to 0 means number is even. If power is even, then I can reduce the power by dividing it by 2. So let us write that code here. So if it is even number, then return, call power function and multiply m into m. So one multiplication, that is m is multiplied by itself for one time, then this will be n by 2. That's good. So number of multiplication will reduce further. Then else means number is not even, power is not even, power is odd. If power is odd, one multiplication is extra. So I will write down return m into power of m into m, comma, n minus 1 divided by 2. If it is odd number, then one multiplication we are taking here directly, and then n minus 1 by 2. So n minus 1, it will become even number, then divided by 2. So let us take an example and trace this function and see in how many multiplications we can get the answer. So I'll take the same example, that is power of 2, 9. So we are looking at this function. This is a new version of a function which is having less number of multiplications. So let us try this. Power of 2, 9. This is 2 and this is 9. So n is 0, no, n is not 0. So n is even, no, it is not even. So it is odd, so it will enter here. So m into so and so. I will write on those things directly here. 2 into power of 2 into 2. So I'll write 2 square. See, this is m into m. So 2 square, comma, n minus 1 by 2. So that is 9 minus 1 by 2. 9 minus 1 by 2. That is 8 by 2. So it will be 4. So I will rewrite it as 4. So 2 square, that is 4, comma 4. So this is the call. Now again a call is made. This time this is 4. That is 2 square. So 2 square and this is 4. So 4 is not 0. 4 is a even number. Even number. Just there is a call with multiplying m into m and n by 2. So let us take a next call, that is power of m into m. M is now 2 square. So it becomes 2 square into 2 square. And this should be by 2. So 4 by 2. 4 by 2. That's what we have to do. So you can see this line. So this I will rewrite. So 2 square into 2 square. This becomes 2 power 4. And 4 by 2. So this becomes 2. This is a new call again. Then let us continue. 2 power 4 and this is 2. 2 is not 0 and 2 is even. So it will enter into this part. So next call, that is m into m. Power of 2 power 4 into 2 power 4, comma n by 2. So this is 2 divided by 2. So I will rewrite this one. So this becomes 2 power 8 and this becomes 2 by 2 is 1. Now this call, this is 2 power 8 and this is 1. This time n is not 0 but even n is. This time n is not 0 and n is not an even number, it is 1. So it enters into odd part. So in that, m into power of so and so. So m is how much? 2 power 8 into power of m into m, that is 2 power 8 into 2 power 8, that is 2 power 16, comma n minus 1 by 2. 1 minus 1 by 2, that is 0. So this is the last call. Now n has become 0. So for 0, it returns 1. So this for 0 value, the return result is 1. This is 1. Now what it will become? 2 power 8 into 1. 2 power 8 into 1. So this is 2 power 8. And 2 power 8 goes here. So this becomes 2 power 8. And 2 power 8 goes here. This becomes 2 power 8. There is nothing. No multiplication is there. Just return. And 2 power 8 goes here. So this is 2 into 2 power 8. 2 into 2 power 8. So this is 2 power 9. And 2 power 9 goes here. So wherever the call was for odd number, there is one multiplication. Even number, there is no multiplication. Simply it returns the value. So finally we got the answer, that is 2 power 9. And total how many multiplications we perform? One multiplication, and here we have taken square of this. This was 2 into 2 actually. So 1, 2, then 3, 4 and 5. Here also one multiplication, 6. So just in 6 multiplication we got 2 power 9. In the previous version for this one, it has taken total 9 multiplications for getting the answer when the power was 9. But now for power 9, this has worked faster and we got the result in just 6 multiplications. So that's all about this power function. So we have a faster version of exponent, that is power function also. The same function can also be written using iteration, that is using loop. So that's again a student exercise. So you have to do it. So we will continue looking at more example of recursions in coming videos. In this video, we will implement power function. We have seen 2 versions of power function. So I will show you the first one. Let us write a function called power for finding power of. Let us write a function called power, which takes parameters m and n. It will raise m to the powers of n. If n is equals to 0, then return 1. Otherwise, return power m is as it is, but n will be reduced by value 1 and it is multiplied by m. This is what the function we have seen. So the same function I have written here. Now as usual, inside main function I will declare a variable r, and to this I will assign power of 2, 9. Then I will print the value of r. That's all. Program is ready. I will run the program. So there was a mistake here. So that's all. A function is ready and I am calling that function. Let us run the program and see the result. 2 power 9 is 512. I should get the result 512. Yes, it's perfect. I will change the values. 3 power 4 is 81. Yes, we got 81, so it's working perfect. I will write another function. We have seen two functions. Another function I have shown you with reduced number of multiplications. I will call that function as power 1, which takes m and n. Here, if value of n is 0, then return 1. Then, if the number is even, that is n mod 2 is equals to 0, means if it is even, then return, call power 1 by passing m multiplied by m and n by 2. Else the number is odd, so return m multiplied by power 1 of m into m comma n minus 1 by 2. That's all. This is the function we have seen. This will take less number of multiplications to find the result. So I will just change the function name to power 1 and let us run the program and see. It should give me 81. Yes, it's perfect. Now if I pass 2 power 9, then what's the result? It's 512. It's perfect. If I save 2 power 8, here I have changed the value. Let us run. 256. Let me try one more value. 9 power 3. Yes, it is 729. So that's all. With power function we have seen both the versions. So you can try this program, you can write the program. Now in this video we will learn about Taylor series. We will learn how to write a recursive function for Taylor series. First of all, we will generate the idea how we can prepare a recursive function for this one. Let us observe Taylor series, then we will devise a method for writing a recursive function for Taylor series. So let me read it out. See, e power x, so for any given value of x, it is nothing but summation of these terms. As many terms as you take, we get more precise value. So here it is n term. So you can continue the summation up to some term, few terms, whatever you want. Here in the example, I have written up to power 4, that is total 5 terms, that is power 0 to power 4. Now, how to write a recursive function for this one? So if you observe, there are 3 operations performed in this one. One is summation of terms, and another one is power of x. X is raised to powers every time. Then in the denominator there is a factorial of 1, factorial of 2 and 3 and 4, so on. So there are 3 values that are involved here. In our previous videos we have already written recursive functions for sum of first and natural numbers, that is sum of first and natural numbers 1, 2, 3 goes on to n. And we have also written a function for finding factorial of n, that is number n, that was 1 into 2 into 3 into goes on to n. And we have written a function for finding power of x power n, that is m power n we have taken. So this is x into x into x into x goes on for n times. We have already seen this. We have already written recursive functions for this. We said that sum of n is sum of n minus 1 plus n. So we have written it like this, sum of n minus 1 plus n. And this factorial of n minus 1 then into n. So we have written it like this, factorial of n minus 1 into n. And this we wrote power up to n minus 1 times. So this was power up to n minus 1 and into x. So we have written these recursive definitions already. Now for Taylor series, actually we have to combine these 3 and write a recursive function for that one. So let us observe few things. Here if you see, the first value n. So the recursive call will start from n and it will be go on reducing up to 1. And then it will start adding. So the addition of values is done at returning time. So actual addition starts from 1 onwards. So if I take the value of 4, sum of 4, then this will call sum of 3 and plus 4. This 4 will be added at returning time. Then sum of 2 plus this 3, sum of 1, then plus 2, sum of 0, then plus 1. The sum of 0 is 0. So while returning, this is 0, then this is 1, 1 is added, then this in this 1, 2 is added, and total is 3, and then here 3 is added and here 4 is added. So you can see that the addition is done at returning time. So similarly, for finding factorial also, product is done actually at returning time. So the starting point will be 1 and the last value will be multiplied will be n. And similarly in the power also. Now for Taylor series, what we want is, we want 3 things: summation and power, as well as we need factorial. So this x is raising to some powers and also we are getting factorial. Now a function for Taylor series must perform 3 operations, but the function can return only one result. Like this is sum of 3 numbers plus 4. Like this is sum of 2 numbers plus 3. So here sum of these terms plus this term we can do. But what about the power and factorial? So power and factorial cannot be returned by a function. Function can return only one value. So when you have to involve multiple values in a recursion, then you can use static variables. So let me show you how we can frame a recursive function for finding e power x using static variables. First, I will try to devise the method, then I will write down a function for that. Let me take the example for e power x for 4 terms, means total 5 terms it will be. So highest degree is 4. Now let us devise a recursive procedure. For that, I'll take the example up to power 4, that is highest power 4. So let me write the function as x and 4. Let us start with this one. So I am first doing the tracing, then I will write down the function based on that. Now what we want, so when it is x comma 4, it should call itself by 3. So okay, it will call itself by 3. Then it should call itself by 2. Okay, then 1, then 0. Now when it is 0, it should return 0. So okay, it will return 0. So the result of this is 0. Now what we need for this term, actually for this function, we are here. So what it should do, x by 1 it should do. So okay, I will write it as 1 plus x by 1. 1 plus x by 1. This is what I want, x by 1. Now this result is returned here. So the result of this function will be 1 plus x by 1. Now for this term, for this function, what I want is x square by 2 factorial, and this should be added. So I need this x and 1 so that x is multiplied with numerator, so it becomes x square, 2 is multiplied with denominator, so it becomes factorial. Then when I go back again here, so this result will be given to this function. So the result of this function is 1 and x square by 2 factorial. Now for this function call, it should be x cube by 3 factorial and plus 1. So in this function call, it should become x cube. So for making it as x cube, I need this x square. So in that I can multiply it by x and obtain x cube, and then I need 2 factorial, so that I multiply it by 3, so it becomes 3 factorial. Now for handling these 2 values, that is numerator and denominator, I take 2 static variables. First is x power, so this is power p I will take, and then next is denominator, that is factorial, so I'll take it as f. Now initially I will write them as 1 1. So assume that this is x power 0 and this is 0 factorial. So we have these initial values, that is for the first term. Assume this. Now let me trace this once again. So I'll remove these and I will utilize these static variables in this recursive calls. Now let us start again. For this function call x comma 4, that is I want total 5 terms, that is highest power is 4. So for this it will call itself with 3, then 2, then 1, then 0. So for 0 it should return 1. So that is this term, that is 1 it is returning. Now when it goes back here, what it should do? I need the term 1 plus x by 1 for this call. So let us multiply this p with x and factorial with 1. So this x and this one, this x and this one, this x is multiplied with p and this 1 is multiplied with f. So this, let us write it as p by f. So this is p by f. So this one is the result obtained by this function plus p by f. So I will write on the steps once again. This is p is assigned with p into x, this I have to do, and then f is assigned with f into 1, this I have to do. Then the result of this one is 1 plus, this is p by f. So p is x and f is 1, so this is x by 1, so this term is x by 1. So these are the two steps every time I will be performing. So I will not write them every time. Directly I will be using this 1 by p power x, and these operations I will perform here. Now let us continue. It goes back with the result. What is the result? The result of this function is 1 plus, what is p by f? P is x and 1. So this is x by 1. Now in this call also it has to perform this. So this becomes into x, that is x square, and f becomes into 2, this is 2, so into 2, so this is 2 factorial, and plus, now in this result it is added. So what is added? P by f. So p is x square and by f is 2. Then the result of this function is returned. The result of this function is returned. So this becomes 1 plus x by 1 plus x square by 2. Now for this function call, again this p should be multiplied by x and f should be multiplied by 3. So it becomes x cube and this becomes 3 factorial. So plus x cube by 3 factorial. That is 6. Now this is the result of this function call. So this returns and this becomes 1 plus x by 1 plus x square by 2 plus x cube by 3 factorial. Now these steps, as I said, I will not be writing them, but I am performing every time. So into x, so p again into x, this becomes p x power 4, and this is into 4, so this becomes 4 factorial. So that term is added and this is x power 4 by 4 factorial. So result of this function will be 1 plus x by 1, x square by 2 factorial, x cube by 3 factorial, plus x power 4 by 4 factorial. So that's how we are getting the result of a Taylor series for highest power 4. Now let me write a function for this one, which is utilizing variables that are static p and static f and x and n. By using these static variables, we will write a function. So let me write the function here. Return type is integer, function name is e, and taking two parameters x and n. Now here I need two variables. So first of all, I declare some variables that are static int p, that is 1, and f, that is also 1. Then I need one more variable. The result of this function is added by p by f. So I have to take one more variable to store the result of a function. So I will take one more normal variable, r. If n is equal to 0, then when n is 0, it is returning 1. Return 1. Else, what are the steps? first call itself. So first is call. So e x is as it is and n minus 1. The result of this function should be taken in some variable. So for that I have taken a variable r. Let it be in r. Then here in the basic step I have shown you that p is multiplied by x and f is multiplied with the value of n. So let us do this. P assign p into x and f assign f into n. So these two things will be happening at returning time. So at returning time the power will be growing. By the time it return back to the first call, p will be having x power 4 and f will be having 4 factorial. So those two are performed in returning time. Now what I have to do? I have to take the result of a function and plus p by f. The result of a function plus p by f. The result of a function plus p by f. Result of a function p by f. This is what I have to go on returning. So return result of a function r plus power by factorial. So this is a recursive function for Taylor series, that is e power x. For the same Taylor series, we'll look at one more approach which is faster method and takes less number of multiplication for getting the result. So I will show you the approach and also I will write a recursive function for that one. In this video, I will implement a function for Taylor series, that is finding e power x, that we have already seen in the previous video. So just I will write a function and just I will give you a demo of that function. Function name I will call it as e, but return type I will take it as double. While explaining on board, I have used integer most of the places, but actually the result is in decimal point, so I should take either float or double. So I am taking double here and the parameters are x and n. See, x is the power of e and n is how many terms we want. So the more number of terms we take, we get more precision. Then inside the function we are using static variables which I will declare them as double, that is p assigned 1 as well as f assigned 1. Then if n is 0, return 1. We need one more variable r for storing the result, so I will declare it as double, and that r assign e x comma n minus 1. And every time p is multiplied by x and f is multiplied by n, that is for denominator and it is a factorial, and return r plus p by f. So that's all, the function is ready. Then from main function I will call it. Directly I will write the result inside printf. Call function 1 comma 10. So e power 1. It should give the result e power 1 and the number of terms that we want are 10. If I want more precision, then this 10 instead of 10 I should give more larger number. Let us run and see what is the output of this function. E power 1 is 2.718282. Let us check it on a calculator. 1 e power x. Yes, 2.718281. So I got the correct result. Let us try with another value. I'll give the value 3 and run it. So the answer is 20.079665. Let us try it here on the calculator. 3 e power x, 20.08557. And here we got 079. So it is little less than that. So if you want more accurate value, then increase the value from 10 to 15 or 20. So you can give some another number. Let us check for 4. It is 54.44. And here on the calculator, 4 e power x, 54.59. So this is little less than that. If I increase the number of terms, instead of 10, I will give 15. Let us see what result we get. Yes, 54.597, 54.598. So still our value is little less than that, so I can still increase the number of terms to get more precise value. So that's all. This function is finding e power x, that is the result of Taylor series. That's all in this video. Now let us take a different approach for evaluation of a Taylor series. And this method will be faster by taking less number of multiplications. So where actually multiplications are done. So for evaluation of factorial, 4 factorial, that is multiplications are more in number, and then x power 4, then x has to be multiplied by 4 times. So there the multiplications are. So for each term we have to perform some number of multiplications. If you analyze for 4 degree 4, that is power 4, total how many multiplications are required? Let us do the analysis. For this term there is no multiplication, and here also there is no multiplication. This term x square, so x into x, so we need 1 multiplication, and this is 1 into 2, we need 1 multiplication. So total 2 multiplications are there. And here x cube, so this is x cube means x into x into x. So these are 2 multiplications, and this is 1 into 2 into 3. So these are 2 multiplications. Total 4 multiplications are there. Now x power 4 means total 3 multiplications will be required in numerator, and I'm just writing multiplications, and here 3 multiplications will be required in denominator. This is 6. So it means next term it requires 8 multiplication and 10 multiplication. So this is how we are getting the multiplication. So if I take 2 common, this is 1 plus 2 plus 3 plus 4 goes on to n terms. So this is summation of n terms. So this is n into n plus 1 by 2, this one, and the result is n into n plus 1. So if you are evaluating a Taylor series for n terms, then total how many multiplications required? N into n plus 1 number of multiplications required. So this is nothing but order of degree of n square. So I can say that n square multiplications are required. Yes, roughly, means it's not exact, you don't have to take exact. N square is sufficient to understand that these are more in number or huge in size. So for evaluation of Taylor series by taking term by term, so for each term some multiplications are required and total multiplications are n square. Can we reduce the number of multiplication? So let us see how we can reduce the number of multiplications. Now I'll show how we can reduce multiplication. So here I can take the terms common. So let us start. I will take up to power 4. So I will rewrite that formula: 1 plus x by 1 plus x square by 1 into 2 plus x cube by 1 into 2 into 3 plus x power 4 by 1 into 2 into 3 into 4. Now in this I can take x as common for all, and denominator is 1. So this is 1 plus, when x is taken as common, so this is x by just 1 into 2. So let us just write it 2 plus x square, x is taken as common and 1 is taken as common. So this is 2 into 3, and plus x is taken as common. So x cubed by 2 into 3 into 4. So I have taken first common term. Numerator and denominator both have reduced. Now let us see if we can take more common values. 1 plus x by 1 and 1 plus, in this I can take x by 2 common. Yes, x by 2 is there. So this is x by 2, and here it is 1 plus, as x is taken, so this is just 1x and 3 plus, and here x is taken, so this is x square by 3 into 4. Then 1 plus x by 1, 1 plus x by 2, 1 plus, here I can take x by 3 common, and this will be 1 plus x by 4. So that's how by taking commons I have reduced the number of multiplications. How they are reduced? Let us see. See here there is 1 multiplication, and this term is multiplied here. So this is 1 multiplication and this is another multiplication. So 1, 2, 3. And if you consider this is multiplied by 1, so let us say 4. So only 4 multiplications are required. So if you want up to 4th term, that is degree 4, power 4, then only 4 multiplications are required. So the number of multiplications has reduced to order of n. It's not square. Earlier that was a square. So now it has reduced to order of n. So yes, by taking commons, we can reduce the number of multiplication from quadratic, that is square, to linear. We have reduced the time. Earlier it was n square. This is quadratic. So the time was quadratic. Now the time is linear. So this is faster. So one observation is by taking commons, we can reduce the number of multiplications. Now, how to write a recursive function for this approach? Now let us write a recursive function for this. Now let us observe this form of Taylor series and let us see how we can devise a recursive function for this one. So first let us observe. If I call this recursively by passing x and 4, then it may be at 4, then it will call itself for 3, then 2, then 1. But if you observe, this result has to be multiplied with this one, plus 1 is added, and the result is multiplied with x by 2, and plus 1 is added, and the result is multiplied. So actually multiplication is done in this form, or actually multiplication is done in this order. First x by 4, then with x by 3, then x by 4. So, and returning time, there is nothing. If you are multiplying and adding 1, multiplying and adding 1, returning time, there is nothing. So usually the recursive functions that we have written, they were performing the operations mostly at returning time. But here at calling time itself, I should find out this term and multiply it with x by 3 and add 1. So I get this term. Then this I should multiply by x by 2 and add 1. Then I get this term. Then this result should be multiplied by x by 1 and add 1. So I get the complete result. So it means when I did for x by 4, so that I should multiply it by 1 and add 1. So actually the processing is done at calling time only. So when the first call is 4, before calling the next call, that is 4 minus 1, that is n minus 1, it should perform the multiplication. So this is happening at calling time. So this can be easily written using loop. So first let me write down how it can be done using loop, then I will show recursion. So let us write a function for loop. Integer e, integer x and integer n. Now in this I have to start from this term, right? This term. So I will take some variable for holding the result. So let us take one variable integer s, that is initially 1. Now what I have to do in each step, x by 4 multiplied by with the result s and added 1, and this becomes a result, and this is multiplied by x by 3 plus 1 and this become a result. So result I am taking it in s. Every time s should be multiplied by x by n, whatever the value of n is. Right now it is 4 if you start from here, then plus 1 is added and this result should be taken in s only. So this is in s. So this step I have to keep on repeating. So for how many times? For n is greater than 0 and n minus minus. That's all. So n is right now suppose 4, then it will become 3, then 2, then 1. So it will get multiplied and finally we get the result. So we can return s. So this is the step perform every time. So if n is 4, so it is performed for 4 times and the result is returned. So this is easily possible using loop. And here I have not taken any extra variable I, because whatever the value of n is, from there I am reducing. So there is no initialization part, just semicolon and the condition semicolon and n minus minus. So if n is 4, then it will become 3, then 2, then 1 and then 0. When it is 0, it will not repeat, but it will return this s. So s is having the result. Now same thing I can write using recursion, but in recursion I have to perform multiplication at a calling time. So at a calling time if I have to do, then I can take the help of static variable now. So let us write it with the help of static variable. So it will be on the same fashion. Recursive function, this is a recursive version, x and integer n. I need one static variable for storing the sum, and whose value is 1 initially, this one. Now if n is 0, means when it has reached 0, do nothing but return s. So here also I will write down s. Else, what I have to do? Else, perform this operation. So the same operation I'll perform. S assign 1 plus x by n multiplied by s. The next is, as it is repeating, so here call itself again by e, x and reduce value of n, that is n minus 1. And here I should write down a statement that is return. That's all. So already we have discussed in our previous lectures that loops will have just ascending, there is no descending, but recursion will have ascending and descending. But this procedure can be performed only in ascending. So I have taken a static variable and I am storing the result in that one at calling time itself. So this is a iterative version and recursive version of a function for evaluation of Taylor series with order of n number of multiplication, that is a reduced number of multiplications. So that's all with the Taylor series. Now similarly there are more series like sine series and cos series. That is your student exercise, so you have to write down the functions. So you try to write down those functions. So here in this video we'll look at a recursive function for finding e power x, that is for Taylor series. We have already seen the procedure using Hanoi rule in the previous video. That same function I will implement here. Already I have a body of a function. I will implement a function. I'll take a static double value s. While explanation I have taken it as integer, but the result is double type or decimal type. If n is equal to 0, return s. Otherwise, s is evaluated as 1 plus x divided by n into s. See, x and n both are of type integer, so I'll get integer division here. So I should typecast it as double, or else I can multiply x numerator with s beforehand, so that this result becomes double, and then divided by integer also gives double. So writing statement will give a perfect result. Otherwise I have to typecast x by n. Now the next statement is return the function called x comma n minus 1. That's all. Inside the main function I will directly print the result obtained by that function. So printf percentile lf, then slash n, call the function e1 comma 10. Let us run the program. We already know the result. Let us see whether we get same result or not. Yes, 2.718282. If I give the value as a 2, yes, it is 7.38871. Let us check it on a calculator. 2 e power x is 7.389 and we got a 388. So it is less, little less. If we want more precise value, then we can increase the number of terms. So that's all the implementation of Taylor series using Hanoi's rule. Yeah, in this video we'll look at implementation of function for Taylor series using iterative method, that is using loop. So already I have the body of a function. I will implement the body. I'll declare a variable s that will be initially 1. Then for iteration I will take one variable I. We need numerator and denominator, so I will take double numerator, that is initialized with 1, and double denominator initialized with 1. Next, for loop will start I from 1 onwards and going up to n, I plus plus every time. Now inside for loop, numerator I should multiply every time by x and denominator should be multiplied by I every time. So I is 1, then I is 2, so we'll get the factorial. Then s should be added with numerator by denominator. At the end outside the loop, return s. So this is a iterative version. Let us print the result obtained by that function, percentile lf, new line, then call function by passing 1, 10. So we already know the result, we should get the same result. 2.718282. Yes, perfect. So this is the implementation of Taylor series for finding the value of e power x for 10 terms for given number of terms. So that's all. Now the topic is Fibonacci series. So here we will learn what is Fibonacci series, and then we will devise a recursive definition and we will write a recursive function for that one, and finally we will analyze that function. So let us start. See, this is the Fibonacci series. The 0th term is 0, next term is 1, then 2, then 3, then 5, and so on. So how we are obtaining these terms? Each term is obtained by adding previous two terms. So that is 5 plus 8 is 13, and this term is obtained by adding these two terms. So initially what are the terms? These are the starting terms. Means if it is 0th term, then it is 0. If it is a term 1, then it is 1. Rest every other term is obtained by adding previous two terms. So initially you must have two terms, then only you can define like this, that every term is obtained by adding previous two terms. Alright, so this can be defined mathematically. Fib of n can be defined as fib of n minus 2 plus fib of n minus 1 when n is greater than 1. If n is 0 or n is 1, then if for 0 it is 0, for 1 it is 1. So if n value is 1, the answer is directly 1. For n is 0, the values are directly 0. For n is equals to 1, answer is directly 1. Otherwise, add previous two terms. So let me put it in a table. Now this is term number n and this is fib of n. Suppose I want to know 5th term, answer is 5. If I want to know 7th term, answer is 13. So first let me write a recursive function for Fibonacci series. Based on this recurrence relation, or based on this recursive definition, I will write a function integer fib of integer n. So here it says that if it is 0, return 0, if it is 1, return 1. So it means if n is less than or equal to 1, return n itself. Means if n is 1, return 1, if n is 0, return 0. Otherwise, return fib of n minus 2 plus fib of n minus 1. This is a recursive definition. That's all. If you want to find out any term like 7th term or 10th term or any term, you call fib of 10, you get the 10th term of Fibonacci series. Call fib of 7, you get 7th term. We'll come back to that function afterwards. So first of all, let us write a iterative version, that is a function using loop. So let me write a Fibonacci function using loop. Integer fib, I'll give the name fib once again, same name I'm using here. Then if the number is less than or equal to 1, then return the number itself. So here, if n is less than or equal to 1, then return n itself. Right? Otherwise, I need two terms to add them one by one. So integer term 0 is 0 and term 1 is 1. And also I have to add the values. So for addition, I will take sum s. So I have three variables. Now using these three variables, I will write down a loop for finding out nth term. See, suppose I have to find 7 terms, then already term 0 is available, term 1 is also available. Then I have to obtain this term 1, 2, 3, 4, 5, 6. So actually I should generate only 6 terms. So I should perform additions only 6 times. Already I have these 2 terms, right? So 2, 3, 4, 5, 6, 7. That's all. So I should start from second term onwards and stop at 7th term. So whichever term I want, I should stop that. So I should start from 2 onwards. So let me run a loop for I assign 2. So I need one more variable I, and I is less than or equal to n and I plus plus. So this is for repeating the procedure for n minus 1 times, or I am starting from 2 to n. Now every time what I have to do, S should be assigned with T0 plus T1. So this term should be obtained by adding these two, that is T0 and T1. Then after getting the sum, now this should become T0 and this should become T1. So for getting the next term, so I should change this value T0 and this I should make it as T1. So T0 should be made as T1 and T1 should be made as S, and repeat this procedure. So finally a result will be in S. So this is a iterative version. So iterative version, what is the time taken by this algorithm or this procedure? This procedure takes, let us take it, this statement will execute for 1 time and 1 time. This loop is written as 1 plus n plus 1, but starting from 2 onwards. So let us say it is only n, and the things inside will be for n minus 1 times, n minus 1 times, and this is 1. So total is 1, 2, 3, 4, 4n and minus 1, 1. So this plus 1 gets cancelled. So it is 4n. So the time is 4n. So it is order of n. Basically, we wanted to know the degree. So it is order of n. So we don't want exact formula. We want the degree. You can see that there is one for loop, and the for loop will repeat for n times. So the time is order of n. It's obvious from the function. So this algorithm takes order of n time. So already we have written iterative version. Now let us go back to recursive version and analyze that one and see how much time it takes, and if any improvement required, we will do some improvements in that. So I'll remove this one and then we will analyze that function. Now let us trace this recursive function for fib of 5. If we pass 5, what happens? 5 is not less than 1, so it will make 2 calls. So we know the function is very simple, so I will just go on tracing this one. So here it will call fib of 3 and there it will call fib of 4 afterwards, not now. First this call will be made, as this is 3, so it will make a call for fib of 1 and fib of 2 afterwards, not now. Fib of 1, this is the end when n is less than or equal to 1. So yes, n is 1 now. So this will not call further and the result is 1. Then here it has to call fib of 2. So I'm just writing f here for fib. Then fib of 2 further calls fib of 0 and fib of 1. Fib of 0 gives the result 0 and this gives the result 1, and they are added, result is returned, and this is added, result is returned. And here it will call fib of 4. So for a fib of 4, this is fib of 2 and this is fib of 3. Fib of 2, fib of 0 and fib of 1. So these results are obtained 0 and 1 and they are added, result is returned. And on this side, fib of 3, again this is fib of 1 and fib of 2. Then fib of 2, this is fib of 0 and this is fib of 1. So here the call is, so here the result is 0 and this is 0 and this is 1, and added, return, added, and final addition is done. So this is how a tree looks like, a recursion tree looks like for fib of 5. If you look at the functions in the order in which they are called, this is the first function call and the second call and the third call, then fourth call, fifth call, then sixth call, then seventh, 8, 9, 10, then this is 11th call, 12, 13 call, 14 call, 15. So for fib of 5, number of calls are 15. Calls are 15. Then fib of 4, how many calls are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 calls are there. Then fib of 3, how many calls are there? 1, 2, 3, 4, 5. 5 calls are there. So now, if we try to observe any pattern, there is no pattern here. This is 5, so this is 15. 5, 3 is 15. Then 4, 3, it should be 12. Then this is 4 into 4 or 2 into 4 plus 1. So we cannot figure out what pattern it is following. So if you want to know the time taken by this one, then assume that this fib of n minus 2 is also fib of n minus 1. So this is calling itself for 2 times n minus 1, n minus 1, n minus 1. So when a function is calling 2 times by a reduced value of 1, n minus 1, then the time is order of 2 power n. So the time taken by this function is 2 power n, approximately 2 power n. So if you observe, the previous function iterative version was order of n and recursive version is 2 power n, too much time consuming. Now, is there any method to make it faster than 2 power n? Let us observe. Now this analysis is important. If you see the tracing tree, that is recursion tree, the value of f3, function f3 is called here, and again it is called here. f2 is called here first time, then again f2 is called, then again f2 is called. So similarly f0 and f1, they are also called multiple times. So a recursive function is calling itself multiple times for the same values. So such a recursive function is called as excessive recursion. So yes, this Fibonacci function is a excessive recursion because it will call itself multiple times for the same parameters. This is the problem in this one. So is there any way to avoid the excessive calls and just make a call only once and utilize it in further calls? So yes, what is the method? Let us devise a method. If you want a function to retain these values so that they can be utilized here, then for retaining the values you have to take the help of static variable, or you can also take global variables. Let us take one array, maybe a static array or global array, whatever you want, you can take it. Index 0, 1, 2, 3, 4, 5, 6, as much size as you want you can take it. So just I have taken some size, we want up to 5. Now how to write now how to modify this algorithm to make it faster? So I'll remove few things from board and show you. This global array or static array, let us initialize it with -1. -1 means we don't know the value, -1. Now, let us trace it once again by taking the help of this global or static array. First, I will show you the tracing, what modifications we can do, then we will modify our function. Let us see. Call fib of 5. Do we really need to call it? Check f of 5. -1. We don't know the answer for this. Okay, call this one. So, when it is called, it will make 2 calls. So, the first call. Fib of 3. Do we really need to make fib of 3? Yes, we have to because we don't know the answer. Then this will make fib of 1. Do we need to make a call for fib of 1? Yes, because it is -1. Okay, make the call. So once you make the call, the result is 1. So once you got the result, because this is a small function, see if n is less than or equal to 1, return 1. So return 0 or 1, whatever it is. So this is 1. So we got the answer. So change this to 1. Now we know the answer for fib of 1. Yes. Then go back. Do we have to make a call to fib of 2? Yes, we don't know the answer. Then do we have to make a call to fib of 0? Yes, we don't know the answer. Call this function. So this result will be 0 as per this one. When it is less than or equal to 1, return the same value. So 0 returns 0. So modify this also. Now we know the answer for those two. Then make a call for this one. Do we need to make a call for this? Check. No, we know the answer. Don't call this. It's not called. Yes. So avoid the call because already we have got the answer here. So this call is skipped. Then I have to get the answer for this one. This was 0 and this was 1. So this is 0 plus 1 is 1. So this answer is 1. So modify this one. We know the answer for this. Then we got this answer 1 and this answer 1 plus 1. So this is 2. So we got the answer that is 2. Then let us go on that side. Fib of 4. Do we know fib of 4? Check it. No, we don't know. So we have to call this one. So if you call this, then there are two calls inside. Fib of 2, do we know it? Yeah, we know it. Don't call this one. So don't call this also. So further calls will also be avoided. Then the result we know how much it is. It is 1. Fib of 2 is 1. Then fib of 3, shall we call it? Check it. No, we know the answer. So don't call this one. So then following calls will also be avoided. And the answer for this one is how much? 2. Then perform addition. 1 plus 2, this is 3. Now we know the answer for this side also, that side also, plus. So this becomes 2 plus 3, that is 5. So this, I did not update this. So now this is 5. We know the answers for all. So these calls are avoided. So if you remove those calls and check 1, 2, 3, 4, 5, 6. So it is making just 6 function calls. For 5, 6 calls. Reason 5, 4, 3, 2, 1 and 0 is also included. So for n, how many calls? N plus 1. That is n to 0. So the time taken by this method will be order of n. So time is reduced. So just now you saw that function, if we analyze, it will take order of 2 power n, that is exponential. I did not analyze it thoroughly, just I have told you that it takes 2 power n time approximately. That is upper bound, 2 power n is an upper bound. But now by storing the result of the function in an array, we have reduced the excessive calls and the time is less than 2 power n and it has reduced down to just order of n. So a big change in the time complexity of Fibonacci function. So this reduction in time is because of storing the values in an array, holding the results so that avoid excessive call. So this approach is called as memoization. Storing the results of the function call so that they can be utilized again when we need the same call or avoiding excessive calls. This approach is called as memoization, means storing the results. So this is applicable here in Fibonacci series. So I have given introduction of memoization. So this is an example, suitable example for memoization. Now based on this memoization, I have to modify that function. So I will remove the function and write a better function that is using memoization. Let us write a function. Suppose there is some global array f which is initialized by some function, let us say main function. All minus 1 are filled in main function. Now Fibonacci function. Fibonacci function takes parameter n, and if n is less than or equal to 1, then in f of n store the value n and also return n. So if you observe, the previous function was having just return n, but now this function is also storing the result in global array for memoization. It is storing in f. Then else part. Else, earlier blindly we were making two functions call, that is fib of n minus 2 and n minus 1, but now we check and then make a call. If value is not known, then we'll make a call. So if f of n minus 2 is minus 1, means if you don't know the value, then f of n minus 2, you get the result of fib of n minus 2. So here we will make a call. Similarly, if we don't know the value of fib of n minus 1 and it is minus 1, that we don't know, then make a call for fib of n minus 1 and store the result in f of n minus 1. Now we have two values, then simply return addition of these two values, that is fib of n minus 2 plus fib of n minus 1. So this version is with memoization. Assume that that global array is initialized with -1 somewhere inside main function before the function is utilized. So that's all about Fibonacci. We have learned that it can be written using iteration, then using recursion, and the time is order of 2 power n. Then we have reduced the time by using memoization. So that's all. In this video, we'll look at a function for Fibonacci series. First of all, I will show you a iterative function that I have explained you in the previous video. I will write a function. I will call the function name as fib. It takes parameter n, that is the term number that we want to find out in the series. So inside the function, first of all, I will write a return 0, because if you see this error message, function is having int return type, but it is not returning anything. So that's what the error is. Control reaches end of non-void function. So to avoid this error, for time being, I will write down return 0. Then later we'll see what we have to return. So this error is gone. Now I will write on the function. I have taken some variables like t0 initialized with 0 and t1 initialized with 1 and s for finding sum, and also we need variable I for for loop. Then the very first thing inside a function is if n is less than or equal to 1, then return same number n. Otherwise, we'll find out the term using for loop. So for loop will start I from 2 onwards, and I reaches less than or equal to n, then I plus plus. So it will start from 2 and reaches up to the term number, nth term. So every time we have to find out sum, that is by adding t0 and t1. Then t0 should get the value of t1 and t1 should get the value of sum, that is new value that we have obtained. By repeating this loop for n times, we get the result in s. So then last statement should be return s. Earlier I wrote it as 0 to avoid error, return s. Here I am getting a warning that s may be uninitialized when used here. If it doesn't enter into for loop, s will not be modified and s is having some garbage value. So let us initialize s with 0, so this warning will be gone. We'll not get any wrong answers due to this, but to avoid this warning, I have just initialized s to 0. Now inside main function, I will directly print the result obtained by that function, %d and new line. Then I will call the function fib by passing 10. That's all. So now the whole program is ready. I will run the program. Yeah, 10th term is 55. Let us see 5th term. Answer is 5 for 5th term. Yes, the 5th term is 5. Then 6th term is 8. Let us try that also. Yes, I got the result 8. So it's working perfect. Now I will write a recursive function for finding Fibonacci term. Let me call the function name as rfib for recursive. Then parameter is n, that is the term number. As we have already seen the code, if n is less than or equal to 1, then return n itself. Otherwise, return rfib of n minus 2 plus rfib of n minus 1. That's all. The function is so simple because it's recursive. It has finished in just 2 lines. Instead of calling fib, I will call rfib here inside the main function. Now let us run program and see what the output is. For this it should get 8. Yes, rfib is also giving 8. Now to reduce this number of calls, we have seen memoization. So I will write on a function using memoization. So already I have one function, that is a iterative function called fib, then the recursive function for Fibonacci. Then next I will write a memoization function for Fibonacci. For memoization function, we need one global array f. So I will take the array size as 10, limited size. If you want larger, you can take it. And inside the main function, I will first initialize this array. Using for loop, I will initialize for I is assigned 0, I is less than 10, I plus plus. If you remember, the array should be initialized with -1. So all these locations I will fill them with -1 because 0 is also a Fibonacci term. So we should have the term, so we should have a number, not a Fibonacci term. So -1 is not a Fibonacci term. So I have initialized this array with -1. Now here I will write down a memoization function. That is a function for finding Fibonacci term using memoization. Integer is the return type, so I will call the function name as mfib for memoization. Then it's taking term number n as parameter. First thing is, if n is less than or equal to 1, then in f of n, assign n itself and also return n. So these are two statements inside a if condition. So I will write them in flower bracket. So this is the body of if. Then else means if the number is greater than 1, then check if f of n minus 2 is equals to -1. If it is equal to -1, then call mfib of n minus 2. Call this function. And whatever the result we obtain, take it in f of n minus 2. So I am writing in a single line. Okay, I will take it in the next line. Then next one, again for n minus 1 also I have to check it. If f of n minus 1 is equal to -1, then call the function for n minus 1 and take its result in f of n minus 1. So call mfib of n minus 1. Once we have got this result, whether the function is called or not called, we get the results here. Then return f of n minus 2 plus f of n minus 1, because the results are kept in a global array f. So that's all. This is a function using memoization. So f is a global array that will help this function to store the results of the function to avoid excessive calls. Now here inside main function, instead of calling rfib, I will call mfib for 5 and I should get the result as 5. I have deleted the breakpoint. Now let us run the program. Yes, the answer is 5. If I call it for 6, then let us see. 8. It's working. Now I will put a breakpoint and debug the function. So you have to count how many function calls it is making. For value 5, it should make 6 calls. I have made the value as 5, so it should make total 6 calls. Run the program. So it has came on this printf function. So you have to watch this watch window and debug navigation to count the number of calls it is making. Let us start. First call, value of n is 5. Second call, value of n is 3. So here you can see the value of n is 3, and here at this place you can see there are 2 calls. So in the previous call, it is in this statement. See, it is in this statement. So 2 calls so far. Then for 3, it has entered inside else block. Then again it is going to call itself for 1, that is 3 minus 2. So this is the third call. For 1, this conditional statement will be true and it will come out of the function after executing this if block. So we are on the third call. Third call has finished. Back on the second call. Now it is entering into second if part of this one. So it will make a call with n minus 1, that is 3 is That is n is a 3, so 3 minus 1, 2. So for 2, it is a fourth call. For 2, it will enter into else part. Then first if, fifth call. Then second if. It has skipped because already the value of 1 is found. So total 5 calls so far. Then back on 3. So it is making a second part. So for 3, this it has finished. Now it's going to call this one. So already fib of 2 is known, so it doesn't make a call. Then back on 5. Now second part of 5. Now this is the sixth call for 4. And for 4, already fib of 2 was known, that is 4 minus 2. So that's why it didn't call this one. Then next, again, this for 3 also, that is 4 minus 1 is a 3. So for this also already value is known. It did not call this one. So total 6 calls so far. Now from 4 it will come out. See, it has not expanded the function call with 4 because already the values were found. Now back on 5th, that is value 5. So it is the first call and it will terminate. So total calls are 6. Only 6 calls it has made and got the result. And if I expand this Fibonacci array, you can see that the values are filled in this one 0, 1, 1, 2, 3. Okay. For 4 and 5, the values are not there because one thing I have missed here, that is inside this, before returning the result, I should fill up the value, that is fib of n should be filled with fib of n minus 2 plus fib of n minus 1. Now let us run the program once again and see how the value of global array f are changing. You can see that the global array is all filled with minus 1. If I continue execution, see, first f of 1 is found. Then f of 0 is found. Then f of 2 is 1 now. F of 3 is 2. F of 4 is 3. Then f of 5 is 5. That's all. So this is how the values are being stored in global array f. So that's all in this video. We have seen 3 different versions of Fibonacci function. One is iterative version and recursive function, and the third one was recursive function with memoization to avoid excessive calls. Now the topic is combination formula. This is also called as selection formula. If the set of objects are given to us, then in how many ways we can select the subset of those objects. This formula is used for finding the number of ways we can select the subset. For example, if alphabets are given to us, A, B, C, D, E, total 7 objects are given, and I want to select only 3, in how many ways I can select any 3 of them? Like I can select A, B, C, or A, B, D, A, C, B. This is wrong. This is the same selection. Interchanging of position will not give a new selection. It's called as permutation. Interchanging position is called as permutation. So there is another formula, known formula called NPR also, but this is NCR, that is combination, that is selection. So this is a known formula. Now, how we can write a procedure or a function for evaluation of NCR? Now, one important thing about this formula is, if the value of n, I am taking it as 5, then C, then R. R can take the values from 0 to 5. So it means I can find the values like 5C0, 5C1, 5C2, so on up to 5C5. So the value of R can start from 0 and the last number is same as n. So I cannot have r greater than 5, that is n itself, or less than 0. Now next thing, how to write a function for this one. So I can write on a simple function for evaluation of this formula. I'll write a function here. Return type of a function is int, and let us call the function name as c, and it needs two parameters that are n and r, integer n and integer r. Now for evaluation of this formula, I should know factorial of n, r and n minus r. So these factorials I can find out by calling function fact. That is, already we have written a function for finding the factorial. We have written iterative version also, recursive version also. So we can use any of those versions and we can find out the factorial of these. So for finding the factorials, I'll take some temporary variables t1, t2 and t3. t1 is factorial of n, and t2 is factorial of r, t3 is factorial of n minus r. So I got all three factorials. Now I have the result, just I can return t1 divided by t2 into t3. These must be in the brackets because both are in denominator. That's all. It's a simple function for finding NCR value for any given n and r. How much time it is taking? Factorial function we have already analyzed, and it is taking order of n time, and this is also order of n, and this is n, and this is a simple statement, so it's constant time, so we can ignore that. So it is a 3n, so 3n means it is order of n, means degree of a polynomial is n. So the time taken by this function is n. It's a simple function. That's all. We can write a simple function for finding a combination value of given n and r. Now next, can we write a recursive function for this one? So for getting the idea of a recursive function, first of all we'll look at Pascal's triangle. So let us see Pascal's triangle. Pascal triangle shows that the values of NCR can be obtained by performing addition recursively. How? Let us see this. First of all, on the top the value is 1. Then on this side extremes are taken as 1. Then this extreme is 1. Then these two are added to get 2, and this is 1. Then this extreme value is 1. And this is 1 plus 2. This is 3. 2 plus 1. This is 3. And this one is 1. This side it's 1. And 1 plus 3, this is 4. These two are added to get 6. These two are added to get 4. And this extreme value is 1. So what these values are, let us see. This topmost value is 0C0. And this is 1C0 and 1C1. See, the value of n is 1, so r can be from 0 to 1. Now this row is for 2. So 2C0, 2C1, 2C2. Then this row is for 3. 3C0, 3C1, 3C2, 3C3. And the last row is 4C0, 4C1, 4C2, 4C3, 4C4. So if you want to find out the combination values for n as 4 for various values of r, you can take it from this row of Pascal's triangle. So from Pascal's triangle we can find out the values of NCR, or else we can use this formula also. So already we have seen a function using the formula, but from the Pascal's triangle can we write on a function for finding NCR value? Let us see. Let us observe Pascal's triangle. See, any value, like example 4C2 is obtained by adding 3C1 and 3C2. And how that 3C1 is obtained? By adding 2C0 and 2C1. And how that 2C0 is obtained is a direct answer. 2C1 is obtained by adding 1C0 and 1C1. So it is recursive. It's recursive. If I call this value as NCR, this value is obtained by adding these two. If N is 4 and R is 2, then what is this? 3, 1. So this is N minus 1. See, R is 2, so it is 1 here. So this is R minus 1. And other value is this one. So N, so this is N minus 1. C, R is as it is. So any NCR value can be obtained by adding N minus 1 CR minus 1 with N minus 1 CR. So based on that, I can define a recursive function here. Let the function name be C and it takes N and R. Then here for a recursion, I should define a small problem. Means when N is 0 or R is 0, what I should do? So for this, you can see here, when R is 0, return 1. When N is equal to R, return 1. So extreme points, those are 1 always. When R is equal to 0 or N is equal to R, return 1. So for small values, these are the small values, 1 are the small values. And when it is 1, if R is 0 or N is equals to R. Otherwise, we will add these two terms and get the result. So else return C of N minus 1 comma R minus 1 plus C of N minus 1 comma R. That's all. So this is a recursive function for finding NCR value, that is combination formula. And this recursive function follows actually Pascal's triangle. So it means if I am trying to find 4C2, it will call 3C1 and 3C2. So for 3C1 it will call 2C0, 2C1. For 2C1 it will call 1C0 and 1C1. And 1C0, 1C1 are directly 1. For 3C0 it will call this one and this one again. So it will make the calls from bottom towards top, that is bottom up calls are made compared to this Pascal's triangle. And whenever it reaches 1, it terminates. That is the last point, because when N is equal to R or R is equals to 0, we are returning 1. So that's all about combination formula. In this video, we will see a demo for combination, that is NCR formula. First of all, I will show a simple function for finding NCR value, which uses factorial. So first of all, I will write on a function for finding factorial, which we have already seen it. So fact function, if N is 0, then return 1, otherwise return factorial of N minus 1 into N. This is a factorial function. Now I will write a function for NCR, which takes two parameters, that is N and R. So inside this function, we have to find out numerator and denominator. First of all, I will write return 0 here. So later on, to avoid this error, later on I will modify it. Inside the function, we need numerator and denominator. So numerator comma denominator, I will take two variables. Then the numerator is assigned with factorial of N. Then denominator is assigned with factorial of R multiplied by factorial of N minus R. Then we have the numerator as well as denominator, return numerator divided by denominator. All these are integer values, so division is also integer. The result of NCR is integer type only. So we don't have to worry about any floating points. So let us look at this function once again, that is numerator is factorial of N and denominator is factorial of R into factorial of N minus R. Now inside main function, I will print the result of that function directly, printf %d, a new line. Call the function NCR by passing 5, 1. 5, 1 is 5. Let us run and see the result. Yes, it is 5. 5, 2 is 10. Yes, we got 10. 5, 3 is also 10. I have modified that. So it's also 10. So it's working perfectly. 4, 2 is 6. Yes, 4, 2 is 6. So this was a simple function just using factorials, and we have few statements here to get the result. Factorial is recursive, but this NCR is not recursive. Now let us write a recursive function for finding value of NCR. So here I write the function. Let us call it as all capitals NCR. It's recursive. I should write down something written here to avoid this error. Next, if n is equals to r, or r is equals to 0, then return 1. Otherwise, return NCR of n-1, r-1 plus NCR of n-1, r. That's all. Here inside the main function, I will make function call for this recursive one, capital NCR. Let us find the value of 4, 2. 4, 2 is 6. Yes, it's perfect. Here I will modify the values. Instead of 4, I will say 5, 2. It should be 10. Yes, it is 10. 5, 3. It should be 10. Yes, it is 10. So that's all. In this video, we have seen a simple function using factorial and also a complete recursive function for finding NCR values. The problem is Tower of Hanoi. First of all, we will learn what the problem is. See here, there are 3 towers given. These are the towers, 3 towers given. And in one of the tower, there are some number of discs kept. 1, 2, 3, 4, 5. So these discs are kept on this tower A. Now the problem is, we have to transfer all these discs from tower A to tower C. So we can just take out all these and keep them there? No. You have to take out one disk at a time. Move one disk at a time. Okay, we will transfer all these disks one by one in B. So first will come, the topmost will come here, then above that, then above that, then above that, then from here we will transfer them. No, you cannot transfer like this. You have to transfer such that no larger disk should be kept over a smaller disk. So you cannot have a small disk kept here and a larger disk kept over it. This is not allowed. So 2 conditions are there. You have to move one disk at a time. Second thing, the larger disk should not be kept over a smaller disk. So by following these 2 conditions, you have to move all this n disk from tower A to tower C. For moving all these disks from tower A to tower C, we may require one more extra tower, so that tower B is given as a auxiliary tower. So we have to move disk from tower A to tower C, that is from and to, and this is for utilization, for helping. So this is using this tower, we are using the tower, that is auxiliary tower. So from is the source and to is the destination, and other one is using. Let us call it as using. So or else you can call the tower names as A, B, C. Now the problem is not so easy. It is believed to be unsolvable problem. There is some story behind this problem. It is believed that somewhere in the world there is a temple, and near the temple these 3 towers are there, and there is a tower with 16 golden discs, and few priests are trying to move this disc from tower A to tower C, and they are doing it from centuries, and if they are successful, then world will end. that will be a doomsday. So there is a story behind this one. So it is believed that these towers and temple is in China or in India. So this was believed as unsolvable problem. But this problem can be solved using recursion. Let us see how recursion helps in solving this problem. So we want what should be the moves such that the disk can be transferred from A to C with the help of B. So we'll take some number of disks and we will try to devise a recursive function. Now we are ready to devise a recursive algorithm for this one. I have taken three problems here. One problem with a single disk and second problem with a two disk and three disks. Let us solve these problems one by one. So the first problem, there is a single disk. So simply move this disk from A to C. So the problem is Tower of Hanoi problem, where only one disk is given and we have three towers A, B, C, and there is only one disk. Then what we are supposed to do? Move disk from A to C, that is source to destination, from to, and with the help of tower B. Though we are not using this B here because there is only one disk, we don't need B, but I am writing it. That will help me write down other procedures. Now when there are two disks, Tower of Hanoi, two disks are given and three towers are there, A, B, C, then what I am supposed to do? See the topmost disk, I cannot move it to C, move it to B. So this topmost disk can be moved to B. So this is a small disk, come here. That is not the destination. That is a middle tower, intermediate auxiliary tower. So that is not the destination. So moving there is temporary or moving there is recursively. So that first step is Tower of Hanoi, one disk from, see this was the source and this was the destination, this was the middle auxiliary tower. Now we have moved it from this source to this destination. We have moved from A to B. So for this single disk, topmost disk, C became an intermediate tower or this auxiliary tower. Actually it's a destination, but we are not moving there. So we are moving here. So this becomes source and this becomes destination, and that becomes a using tower or auxiliary tower. So C I will write it in between. Then first step is over. Now second step, move this larger disk from here to C. One disk from A to C directly. So that step is same as this one. So move disk from A to C using B. So though we have not used, but we are saying that we are using B. So the other tower, auxiliary tower, we are mentioning it. So this is move from A to C. That is same as this step, first step. We have already seen how to move one disk. That same step is useful here. Now what is remaining? From tower B, we have to move a disk to tower C, and this becomes an auxiliary tower. So that step is recursive step. So let us call it as recursive step. Tower of Hanoi, one disk, and the source is B, destination is C, and auxiliary tower is A. So these are the three steps I got. So here I am saying move disk, right? Then what about this? This should be performed as per the first step, and this also should be performed as per that first step. So this is recursive. So this definition I have written recursively. Now if there are three disks, how to move them? Let us see. Tower of Hanoi, three disk, source tower, intermediate tower, destination tower. Now we have three disks. How to move three disks? If I number them 1, 2, 3 from top, then how to move them? Now for those steps, we will use a trick here and define recursively. Observe this. I'll say that move these two disks to tower B. Move these two disks to tower B. Two disks we cannot move at a time. No, we are not moving two disks at a time. those two disks are moved by following this method. We already know how to move two disks. We saw how to move two disks from A to C. The final disk was kept here, right? So A to C, how to move we saw. Now instead of A to C, you have to move them from A to B, right? So that is not in one step, that is in 3 steps. So moving two disks from tower A to tower B takes 3 steps, which will utilize a tower C or B, somehow they will be moved. So how to move, if you want to see that, follow these steps. So to make this problem simple, we are saying that move two disks. So moving two disks is not just one step, it is recursive. So how to move two disks? Already step is given. Then again, how to move one disk? Already step is given here. So let us write down that first step. First step is Tower of Hanoi 3 minus 1, 2 disk. From where to where? A to B. A to B. And C is the intermediate tower. Okay, when two disks are moved there, now third largest disk is remaining. Move this disk to tower C. Third disk. So second step is move disk from A to C using B. So move that one. Though we are not using, or we are using it or not, there's a different thing. Using means the intermediate tower. Now what is remaining? You have to move two disks from B to C. Two disks you cannot move at a time. But how to move those two disks in multiple steps already shown here. So follow those steps. Now source is not A, source is B and destination is C. So A is an auxiliary tower. So this involves multiple steps, but we write it as a single step here. So the third step is Tower of Hanoi, two disks from B to C using A. That's all. So these 3 steps, so we can see that when we have 3 disks, we can perform it like this. So now from this 3 disk formula, now from this 3 disk procedure, we can generate the idea for n number of disks. So suppose this is n, then what it should be? N minus 1. Then what this should be? N minus 1. That's it. Because this is recursive, recursion will call itself again. So there are more steps below that call. So don't imagine it's a single step. But we are able to define it recursively. So for defining it recursively, I made a simple problem, the next little bigger problem, then little bigger problem. Now this is suitable for all n number of disks, not just 3 disks. It is suitable for any number of disks. So I have converted that into n. Now I will write down this as a recursive function, and I will take an example and trace this function and show you really these steps will solve the problem or not. Now here is a recursive function for solving problem Tower of Hanoi. Based on our discussion, the final function that I got, the final algorithm that I have written it as a function. So let us read it out. So it is taking 4 parameters, number of disk, tower number. A, B, C are first 3 tower numbers. A, B, C are 3 tower numbers. Then if number of disks are more than 0, then perform these 3 steps. So first step is recursive call with 1 reduced disk, that is n minus 1, and towers are changing. See, this was from tower and this is to tower. So this is using. Now in the first step already we saw that we will move this disk from A to B. So from tower is A and B tower is 2 and C is using tower. Then move a disk from A to C. So I wrote it like this because of lack of space. Then next one, you have to move n minus 1 disks which were kept in B from B to C. So source is from is B and destination is C and A is auxiliary tower. So I will trace this one and see how this function will solve Tower of Hanoi problem. And this is an example problem. Here the number of disks are 3 and tower A, tower B, tower C I'm not calling them as A, B, C. Actually, those are variable names. So values in them are tower 1, tower 2, tower 3. So 1 and 2 and 3. So slight change here. Those are actually variable names. But in them, the values, the name of the tower, I have to take it integer. Otherwise, I should take them as characters. So instead of characters, let us take integer. So tower numbers are there. 1, 2, 3 tower numbers are there. Now, if this function is called by passing these parameters 3, 1, 2, 3. So this is N and this is A and this is B, this is C. So these 4 values are passed. So now let us trace this one. So here the first call, I will write it as a first call. Number of disks are 3 and the tower numbers are 1, 2 and 3. So these 4 values are passed. N is greater than 0, yes, N is a 3. Then what to do? Call itself by N minus 1 and the values are changed. So let us write down this call. So this is N minus 1. This is 2. First is A. A is 1. Next is C. So C is 3. And last one is B. That tower number is 2. Yes, these are changed. Now this call has to be expanded, but before expanding, I will write down other 2 steps also. It will be easy for writing. Print, move from A to C. So A to C. So this step is from 1 to 3. So move a disk from A to C. So A is 1 and C is 3. Then third step. This is step N minus 1. So 3 minus 1, that is 2. And B first, so that is 2. Then A next, that is A is 1. And last one is C, that C is 3. So as we know the working of recursion, this call is making 2 more calls. So first call has to be finished first, then it will print this one, then it will call this one. So we know that, but we have written all of them together at once, so that's easy to write. Now let us continue. This call will be performed. So as per this call, again 3 steps, because this is 2 and 2 is greater than 0. So for that, what are the steps? So first step, A, C, B. So this is 1, A, C, B. Right. The next, print AC. Print AC. So 1 to 2. 1 to 2. See, it is not a... So last tower is not 3, it is 2. So 1 to B, it means A to B. Then this is step 1. And this is BAC. 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 3, 1, 2. This is the call. Then I'll expand this one also, though this is done afterwards. Let us expand this. So for this, first call, ACB. So this 2 will become 1. A, C, B. The next step is move A to C. So what is A? 2. C is what? 1. So 2 to 1. Then third step, N minus 1, BAC. N minus 1, BAC. So 1, 2, 3, BAC. Middle one is B. See, as per the variable names, you see the variable name ABC. So this is A variable name and its value is 2 now. This variable name B and its value is 1 now. So we take the values of the variables. So this BAC are the variable names. So this is B variable and this is A variable. This is C variable. This is written. One more level of steps I have to write, but this time the call will be for 0. 0. Now when it is 0, it has no meaning, because when it is greater than 0, it is performing. So next step will not be performed. So this call will not execute at all. So checking the towers and writing them is useless. So I will avoid writing the steps. So if I have to write, the first step is ACB, that is ACB, that is 1, 3, 2. Though it's of no use, it's going to terminate. So I will avoid this one. Then what is the next step? Printf A to C. A is 1, C is 3. 1, 3. The next step is again 0 with some values. Then for this step is 0 with some parameters, and this is move from 3 to 2. So 3 to 2. This is 1, 2, 3. A is 3 and C is 2. So 3 to 2. And this step is again useless. Now for this, left hand side is useless because the function will not execute. Then middle step, move A to C. So 3 to 1. Move A to C, that is 2 to 1. So 2 to 1. And this step again of no use. Then here, left hand side of no use, middle one, A to C, 1, 2, 3, 1, 2, 3, then right side 0. So actually these steps will not be performed, these will not be performed. So I'll just mark them to show that these are not required. Now let us see how these calls are made and take those results. See, first this is the call, first call, then second call, then third call, then fourth call, which will not execute, so I marked it as, which will not execute, so I have striken off that. Now next step is 1, 2, 3. So the first step is 1, 3. This is the first step. Then this is the fifth call. Then go back. This step is performed. So the step is 1, 2. So 1, 2 is the next step. Then this call, sixth call. Then seventh call. Then this step 3 to 2. So this is 3 to 2. Then eighth call. Then go back. And this is step 1, 2, 3. 1, 2, 3. Then next, this is the ninth call, and this is the 10th call, 11th call, then 2 to 1. So this is 2 to 1. Then this is the 12th call. Then this 2 to 1 is printed. Oh, sorry, this was 2 to 3. I wrote it as 2 to 1. A to C, 2 to 3. So this is 2 to 3. Then 13th call, 14th call, and then this 1, 2, 3 step is 1, 2, 3. Then this is the 15th call. So total 15 calls it is making for 3 disks. But let me show you the values once again. See, first call is this one, then this call, then this call, then this call, then this value is printed. So first this value is printed, then this call, then over, then this is the next value printed, then goes back, and this is the next value printed, and this one is printed next, and then it comes on this side. So 2 to 1, and then 2 to 3, then finally 1 to 3. So the values are printed like this. So if you know the tree traversal, this is more like in order traversal. So the printing is done in order traversal. So these are the steps I got. If I follow these steps upon this problem, then the disk will be transferred from tower A to tower C with the help of tower B. So I will take these steps and show you how it works. But before showing you that, let us analyze how much time this is taking. See, there are 3 disks. Number of disks are 3. So how many calls it is making? This is making 15 calls. When n is equals to 2, how many calls it will be making? So let us look at the subset of this one. So 1, 2, 3, 4, 5, 6, 7. So it is making 7 calls. So actually for 3 itself, if you see 1, then 2, then 1, 2, 3, 4 calls, then 8 calls. So this is nothing but 1 plus 2 plus 2 square plus 2 cube. So these many calls it is making. So this is nothing but 2 power 4 minus 1. That is 16 minus 1, 15. So for n disk, how many calls it will make? I'll write them here. 1 plus 2 square plus goes on to 2 power n. So this will be 2 power n plus 1 minus 1. So this is order of 2 power n. So this is exponential time taking problem. The function is calling itself 2 times by decreased value of n minus 1. So 2 times it is calling 2 power n. So this is time consuming function. It's exponential time taking function. It takes 2 power n time. Now I will take these steps and show you how the disk can be moved. Now here are the steps that we got from the function, and here is a problem with the 3 disks and the tower numbers. You can see I have labeled them as 1, 2, 3. You can call them as ABC also. The value of A is 1, B is 2 and C is 3. So I have taken numbers, and these steps are giving numbers. Now let us follow these steps, perform these steps over this disk and get the result. First step, what does it say? Move a disk from tower 1 to tower 3. So from tower 1 to tower 3 we have to move a disk, and we know very well that we have to move only one disk, right? No need to ask how many disks. We have to move one disk only. So one disk, move it from this tower to this tower. Tower 1 to 3, 1 to 3. Second step, move a disk from tower 1 to 2. So from tower 1 to 2, which is the disk? Now the second smaller disk we have, so move that one to tower B. Over. That is from 1 to 2. The next step is 3 to 2. So third tower to second tower. Okay, move this disk from third tower to second tower. This is moved. The next step is move a disk from tower 1 to 3. From tower 1 to 3. So this largest disk, you send it on tower 3. Okay. Largest disk is sent on tower 3. Now, next is move a disk from 2 to 1. So from second tower to 1. So this smaller disk, you bring it here. Then move a disk from second tower to third tower. Second tower to third tower. So this second largest disk, that is middle disk, you send it on third tower. Then move a disk from 1 to 3. So from first tower to third tower. So move a disk from first tower to third tower. That's all. I have followed these steps and all the disks are moved from here to there. See, the definition was recursive, saying that move 2 disks from tower A to tower B. Really, we were not moving 2 disks in one step. We were moving them recursively. So we have utilized one or the other towers and we have shifted the disk here and there. And finally, we got all 3 disks in tower C. So that was the objective. If you're not following the steps, if you're randomly trying to do, we may be wasting our time by performing unnecessary steps or repeating steps. That is the problem. Now recursion gives us perfect minimum number of steps, exact number of steps. If you follow that, you can move the disk from one tower to another tower. Now that's all about Tower of Hanoi problem. Now for you to remember it, you have to work on this one. So practice this one once and then you can easily remember this one. And this idea will help you solve other problems. This Tower of Hanoi idea will help you think recursively. In this video, we will have a demonstration for Tower of Hanoi problem. So I will write down the function, recursive function, which we have seen. Void TOH, Tower of Hanoi. First is number of disk and next is tower number. So first tower number will be A, the next tower number is B and next is C. Now first is if number of disks are greater than 0, then only perform these steps. So the first step is Tower of Hanoi, call itself for n-1 disk and see these 3 tower names. A to C we have to move using B. So here first move from A to B but using C, so C should come in between. So this is the first recursive call. Then printf, so here I write statement move. See, instead of writing move, I'll do just one thing. I'll just write a order pair, %d, comma, %d, These are the order pairs that we have generated at last. So slash n this one. Now here the tower is A and destination tower is C. This will print order pairs. Then that is from tower to tower, that is source tower to destination tower. Then tower of Hanoi is recursively called for n-1 disk, and here we have to move the disk from tower B to tower C and utilize tower A. So tower A comes in between. So that's all. This is a very simple function. Now inside the main function I will call tower of Hanoi by passing 3 disks, and the tower numbers I will give them as 1, 2, 3. So first value is number of disks, then remaining 3 values are tower numbers. Let us run the program and see what the output we get. See, 7 steps we got for moving 3 disks from tower A to tower C. These are the steps which we have already saw them in the previous video. Also, I have used these steps for moving the disk from tower A to tower C. So the program is just giving the steps to be taken for moving the disk. It is not moving the disk, it is giving us a step. So following those steps, we should move the disk to solve this problem. If I change the number of disks to 2, let us see what happens. See, move a disk from tower 1 to tower 2, then 1 to 3, then 2 to 3. That's all. These are the steps we have seen for 2 disks. If I give the number of disks as 1, then what happens? So directly from 1 to 3. There is a single step for 1 disk. Move a disk from tower 1 to tower 3. So if I give 4, then let us see how many steps I'll get. Yes, these many steps are there. I guess these are 15 steps total. So you can count them, you can check it. That's all about Tower of Hanoi problem. Yeah, in this video, I will show you the solutions for the questions given in quiz. So I have some questions in the quiz upon recursion. So let us solve them, right? I will trace and solve them. So hope you have done it already. But just to confirm your results, or if you have missed anything, so you can understand where you have gone wrong. So let us do it. I have first question here. This is the first question. This is a recursive function. And this is called for f of 1. So we want the result, what the function will return. What is the result of a function if it is called for 1? So this is a function. Okay. Recursive function, how to trace, already have shown you. So the tracing tree will be prepared, right? So let us start preparing tracing tree. F of 1. So first is f of 1. Then inside the function, if you see, there is a static variable. So already in one of the video I have discussed about the static variables in the recursive function. They will maintain only single copy. So this I, only one copy will be maintained. So don't put it in the tracing tree, separately keep I here. So this is a, treat it just like a global variable. So its value is 1. That's it. Now start. If n is greater than or equal to 5, then return n. N is what? Now 1. N is 1. And it is not greater than or equal to 5. The next step, n assign n plus I. So I will change it. N is what? 1. So 1 plus I. I is how much? 1. So n becomes how much? 2. This is 2. N is 2 right now. Then I plus plus. So where is I? It is static. So here it should become 2. I am writing it here. So I became 2. Then return. Return what? F of n. So again the function is called for the value of n. So this is a recursive call. So I plus plus is there. So I have not shown it here. If you want, you can show it, right? So I am showing all the steps now. This one and this one and this one. Now next is call for 2. N is 2. Function is called again for 2. Then this is the declaration. This is over. Because it is static, it is done only once, right? So it is not done again. Again, don't think that I becomes 1. If you're doing it, then you get wrong answer. That is static. It is done only once. Now, right now, the value of I is 2. we are not in the first call, we are in the second call. Yes, that is static, it remains as it is in the second call also. Yes. Then n, is it greater than or equal to 5? Is it greater than or equal to 5? No. Then these three steps. So first step is what? N assign n plus I. N plus I. What is n? 2. What is I? 2. So how much is n now? N is 4. The next step is I plus plus. So I plus plus, I'll make this as 3. Then next, call again itself for fun of n. What is n right now? 4. 4. Now let us do this step quickly. This is over already, right? I is right now 3. N, is it greater than or equal to 5? No, it is not greater than or equal to 5. Then n assign n plus I. N is how much right now? 4. So 4 plus I is how much? 3. So this is how much? 7. Then I plus plus. So I plus plus makes this as 4. Then call function f of n. What is n? 7. Now it comes here with 7. 7 greater than or equal to 5. Yes, it is greater. So do what? Return n. What is n? 7. Return n. So 7 is returned here. Then in this statement, if you see, this was the statement, right? So what is written here? Return. So whatever the result is obtained, that is returned. So 7 is returned from here also. So it is 7 here. Then again, this is the same statement. Same statement. From here only we have called. So return from here also. So this is return. So this is 7. So finally, the answer for this one is 7. So the result of this function is 7. So if you have not maintained a single copy of I, then you might have got wrong results, right? So this is the result, that is value 7. So answer for this is 7. Let us look at second question. So here is a program, that is second question of quiz. It is a little lengthy. Let us trace this program. See, here is a main function and also a function foo. So main function is calling foo. So let us look at the data members or the variables of main function. So what are the variables of main function? A, which is having value 2048. Then sum, which is having value 0. And these belongs to main. I'll write them here. This belongs to main. Now main function call foo by passing a and sum. A and sum. So a goes into n and sum goes into that sum. First and the foremost thing, is it called by value, called by reference, or called by address? What it is? This is called by value. Here stars are not written, so this is not called by address. Ampersands are not there, so this is not called by reference. This is called by value. So let us trace this function foo now. So here foo is called. So first value a is 2048 and sum is 0. So two variables, n will have 2048 and sum will be 0. Then if n is equal to 0, return, it's going to stop. Return means stop, and this is void type. It's not going to return any value. Return means just stop. Then how many steps are there? 1, 2, 3, 4, 5 steps are there. So let us perform these steps. First step, k assign n mod 10. So what will be the value of k? Mod 10, how much it is? If you divide this number by 10, then the remainder will be 8. So mod is 8. The next step, j assign n divided by 10. So j assign n divided by 10. So n is 2048. So when you divide it by 10, 8 will be gone. It will be 204. So j will be 204. Sum assign sum plus k. So what is the value of sum? 0. Sum plus k. So 0 plus k. So sum will be 0 plus k is how much? 8. So sum will be 8. The next step, call itself for j and sum. Call itself for j, that is 204, and sum is how much? 8. Then one more step, print k. So this step will not be performed now because it has called itself. So this will be performed at returning time. So we will do it at returning time. So I'll just leave a line here. Here we have to print k. So whatever the value of k, that it will be printed. Not now, at returning time. So let us continue with this call now. This call. In this call also same steps, right? Same steps. So k assign mod 10, j assign divided by 10, and in some k is added. So k assign mod 10, so 4. J assign divided by 10, so 20. Sum assign sum plus k. 8 is a sum plus 4, so this is 12. Then call itself for next values, that is j and sum. So 20 and 12. And also print. That printing will be done afterwards. So all the steps I have done. 1, 2, 3, 4, 5. 1, 2, 3, 4. Fifth one will be done at returning time. Now continue. This one, this call. It will make this call. Again these steps. So k assign mod. So 20 mod 10 is how much? 0. And 20 divided by 10 is how much? 2. So it gets 2 times divided. Then sum assign sum plus k. Sum is 12. 12 plus 0 is 12 only. Then call itself for j and sum. So 2 comma 12. And also it has to print. I'll just remove this. It has to print. Print will not be done now. It will be done afterwards. Now one more call. So this one. Again those steps. K assign n mod 10. 2 mod 10 is how much? 2 only. J assign n divided by 10. 2 divided by 10. So j value will be how much? 0. Then sum assign sum plus k. So sum is right now 12. So in that 2 is added. So this becomes 14. Then one more call with the foo. So I have to remove this also, right? To just make a space. You know very well about this. Then foo, one more call. What is that? J and sum, 0 and 14. And also it has to print. This will be done afterwards. Now this call, when it comes here, n is equals to 0, return. This has stop. It will not call further. This will stop. This call will not go further. So it will come back to this call. So what it has to do remaining? Print k. So what is k? 2. So 2 is printed. Then this finishes. This is the end, right? This is the end. Then go back to the previous call and perform this step. So what is that step? Print k. How much it is? 0. So this is 0. Then this finishes. Go back to the previous call in this one. So this is remaining. Print k. What is k? 4. So print 4. Then go back to the previous call. This is remaining. So print k. What is k? 8. 8. 2048. And this function ends. Function ends. So this tracing is over. It returns back to the main function. This is the main function. From here it was called foo. From here it was called. Now, next step. Print sum. Which sum? Main function sum. How much it is? 0. This is not change. No, it became 14. This was belonging to foo function. It doesn't belong to main function. Main function sum is 0 only. It is called by value. It is not modified. So print sum is 0. Yes, this is the answer. 2048 and 0 is printed. If you got this answer, then it is perfect. If you got the answer that is 2048 and 14 means you have mistaken. You thought that this sum is modified. We are adding this one. No, that is belonging to foo function. It's nowhere related to this. So this is not modified. So that's all. This is the tracing. This is little bit lengthy, right? Because so many operations are there in the function and the result is 2048 and 0. Now let us look at third question. Let us look at the third example, third question from quiz 1. This is the program given there, this is the example. So let us study this one. See, this is the main function. I have not given in the question, but for explanation I have written it here. In description it's everything is there. So it says that if p is having value 5 and it is passed one value by a reference and other value by value. So yes, p is there. This belongs to main function. So let us draw it. Okay, p is having value 5. Then function f is called by passing p 2 times. But the first time is by reference. You remember this reference, right? C++ reference. Then this is by value. One is by reference, other one is by value. So those two are passed. So it is nothing but P only passed. Now these are the statements. So let us trace this one. So I will write on that function f. Okay. First one is x and the second one is call by value. See, in the tracing of function, if it is by value, I have directly written the value. So what is the value of a p? 5. So that c will have the value 5. So let us write 5 here. Okay, I don't have to write c. But that x is a reference. Don't write 5 there. If it is reference, don't write it. So that x is nothing but referring to this p only. This is p only. That p actually belongs to main function. This is the important thing in this function. If you have understood this, then you can trace it perfectly. Now let us trace it. First step, c assign c minus 1. So what c becomes? C was a 5, right? Minus 1 means c becomes 4. If a c is equals to 0, no, otherwise it should return 1. It's not 0. Then x assign x plus 1. So x assign x plus 1 means x will increment. So what is x? This one. So this should increment and it should become 6. I made it 6. Then call function fun by f of x comma c. Call again itself by passing f of x comma c. C is what? 4. Then why I'm writing x? Because that x is nothing but reference to this p. It's a reference to this p. Every time when I say x, I will come here. Okay. Then into x is there. So I will keep it as it is. I will not take the value and multiply because it will not be multiplied right now. When the multiplication will be done, at returning time it will be done. So because this is done after getting the value, then you can multiply. Otherwise, if you want to multiply now, right now x is how much? 6. 6 into what? What you will multiply? So first of all, this value should be there, then it can be multiplied. So don't write 6, let it be x only. That time only we will see. When it has to multiply, that time it will go to p and get the value. Okay, so leave it as it is. Now this call we have to continue further. So this was the first call I have explained in detail. Now remaining calls, just I'll repeat them. X comma 4, c assign c minus 1. So c becomes how much? 3. Then c, is it 0? No. So x assign x plus 1. So x assign x plus 1 will make it as 7 because this x is nothing but this one. Then call itself again by passing x comma c value is 3 and into x. One more call. Then in this call again c assign c minus 1. So c becomes how much? It is 3, so it becomes 2. Then next is x assign x plus 1. So this becomes 8. Then again it will call itself x comma c is 2 into x. We will see it afterwards. Then again call. So x comma 2 assign 2 minus 1. So c becomes how much? 1. C, is it equal to 0? No, not 0. Then enter inside x assign x plus 1. So x becomes how much? X assign x plus 1. So this x is nothing but p only, right? You remember? 9. Then again call itself by passing f, and that is x comma c is how much? 1. Then into x. I'm keeping it x only at every time, right? I'm not taking the value. Then this one, x comma 1, x comma 1, c assign c minus 1. So c becomes how much? 0. Is the c equal to 0? Yes, c became 0. Return 1. So this function returns 1. So now from here it will return back. So this returns means the same function value becomes 1. 1 into x. What is x now? 9. 9. This is 9. This 9 is returned. So this is the result. This is 9 into x. Now you go to x. What is x? 9 only. So this is into 9. So this is 9 square. So this is returned to this one. So this is 9 square into x. What is 9? X, right? 9 only. So this is 9 cube. And this is returned. So this is 9 cube into x. What is x? 9 only. So this is 9 power 4. And this is returned. So this is 9 power 4. Yes, this is the answer. So the answer returned by, so 9 power 4 is 6561. So yes, this is the answer for this question. Now, if you got wrong answer means you have not done it properly. You have not referred to this one every time. And one more reason of getting wrong answer is you are writing the values here. First time it was 6, then you wrote 7, then 8, then 9. So 6, 7, 8, 9. So you are multiplying these values, so it's wrong. And one more mistake that you may be doing it, you are increasing up to 10. Here also you are doing it up to 10. So commonly this type of mistakes are possible if you are not solving it properly. So this is the answer for this quiz question. Next, we will go to the next question. Now, next quiz question is this one. A function is given and we have to find out what is the result of this function if it is called for 5, value 5, by sending value 5. So we have to trace this one. Let us do it. First time I am sending 5. So fun of 5. Fun of 5. Then these are local variables. Yes, these are not static. So in every call, x will become 1. Remember this. K is also newly created in every call. Okay, we will use them. N is equal to 1, return x. No, it is not 1. Then, for k assign 1 to less than n. 1 to less than n means 1, 2, 3, 4. So for k assign 1, 2, 3, 4, these statements are repeated. So 1, 2, 3, 4, so many times they are repeated. So let us do it. This is x assign x plus what? First one. First one is what? Fun of. K value is what? K value is 1. So this is fun of 1 comma n minus 1. So what is n? 5. Fun of 1 into fun of 4. Then plus, because this is going to be added into x every time. So again one more time. So that time k is how much? 2. Right now k is 2. So this is fun of 2 into fun of 5 minus 2. That is 3. Then plus. This is in for loop. Repeat. One more time. One more time. So this is, I'll continue here. There is no space. So fun of k will be what? 3. So this is 3 into fun of 5 minus 3 is 2. Then plus. One more time. Now this time k will be 4. So fun of 4 into fun of n minus 1, that is n minus k, that is 5 minus 4, it is 1. So many calls for just fun of 5. So many calls are there. This is complex. You cannot solve it easily by using pen and paper. So in this you should finish this one, then this one. So don't know how much expansion this will take, and this one and this one. All these you should know, then multiply and get the result. So this is not easy. It's not easy. Then how to solve it? So for solving this one, we'll take another approach. Let us see this one. So here I will take the values of fun of n, and for the values of n, so I'll make it as a table. Let us do it. Then I'll tell you why I'm taking table. So first, see what is the minimum value? N is equals to 1. If n is equals to 1, if I call this function by passing 1, not 5, if I call it by passing 1, then what happens? Let us get that value. Okay, so first we will find smaller value. Then slowly we'll increase and get the value for 5. Yes, that is the idea. So when n is 1, what is the result? Return x. What is x? 1. So it is 1. Answer is 1. So now we know fun of 1 is 1. Fun of 1 is 1, right? The next, fun of 2. We need this also, right? So I'm not making a tree. I'm making a table. So let us find fun of 2. So fun of 2 means what? So 2 means it is not 1. It will enter here. So how many times this loop will repeat? K as 1, right? K as 1 up to less than 2. So it will repeat only for one time. So let us do it. So for fun of 2, it will be x plus, right? Fun of k is what? 1. K is 1 into fun of 2 minus 1. K is 1, right? Only one time it will repeat. Just observe that, right? There is nothing to explain. You have to read and understand it. So this for loop will repeat for only one time. That statement I wrote here. So what are the values? It's only this much, that's all, only one time. So how much it is? This is x is how much? 1. Fun of 1. Here we already know fun of 1 is 1. Okay, take it as 1 into fun of 2 minus 1. 2 minus 1 is what? 1. This is 1. Oh, this is again fun of 1. Already we know it. How much it is? 1. So this is 1 plus 1 into 1. So 1 plus 1 into 1 is how much? 1 plus 1, that is 2. Yes, fun of 2 is 2. So we got the result. So we have fun of 1 also, fun of 2 also. Let us find fun of 3. Let us find fun of 3. 3. So fun of 3. When it is a 3, x plus, it is not 1, so it will enter inside. So this k takes values from 1 to 3. So how many times it will repeat? 1 and k less than 3 means 1 and 2. 2 times it will repeat. So k will take 2 values. One time 1, second time 2. Let us put it here. So x plus fun of k is 1 and fun of n minus k. So what is n? 3, right? 3. So 3 minus 1. Plus, one more time it will repeat. So plus, it will be accumulated in this one only, added in this one only. So this time, fun of k is how much? 2. Take it as 2. So this is 3 minus 2. So fun of 2 into fun of 3 minus 2. Okay, I'll remove this. So now let us solve it. This is 1. Okay, 1 plus fun of 1, we already know it is 1 into, what is this? Fun of 3 minus 1. 3 minus 1 is 2. Fun of 2, what is the value of fun of 2? We know it. See, this is the benefit. We already know smaller value. So this is 1 into 2 plus fun of 2. It is 2. Just now we wrote it. 2 into fun of 3 minus 2. 3 minus 2 is how much? 1. Fun of 1 is what? 1. Then total how much this is? 1 plus 1 into 2, 2 plus 2 into 1 is 2. So this is 5. So we got the answer as 5. So this is 5. Now next is fun of 4 and then fun of 5. That's how you can get it. Now for fun of 4, I will not write all these things. Directly I will write on the answer. Okay. Then also for fun of 5. So I'll remove this and I will use this place. Fun of 4. 4 means k takes values from 1 to less than 4. So k is going to take the values 1, 2 and 3. So let us start. X is 1. First time fun of 1 into 4 minus 1. So f of 1 into 4 minus 1. So 4 minus 1 is what? 3. Plus f of k is a 2 now. So into 4 minus 2 is a 2. Plus f of 3. K is 3 right now. So 3 means f of 4 minus 3 is 1. So how much this is? So let us add this. This is 1. Fun of 1 is how much? 1 into fun of 3 is how much? What? 5. Plus fun of 2 is a 2. So this is 2 into 2. Plus fun of 3 is a 5 into fun of 1 is 1. So how much this is? 5 plus 5, 10. 10 plus 4, 14 plus 1, 15. So this is 15. Then fun of 5. Fun of 5 is how much? 1 plus. Now k will take the values 1, 2, 3 and 4. So f of 1 is 1. F of 4 is, see it is like this, 1 is multiplied with 4. So f of 4 is 15 plus 2 with 3. So 2 with 3 means 2 into 5. 2 into 5. Then plus, then 3 into 2. So 5 into 2. 5 into 2. If you have observed this, then you can directly write this. Then 4 into 1. So 15 into 1. 15 into 1. How much this is? 1 plus 15 plus 5 to 10 and 5 to 10 and this is 15. 15, 15, 30, 40, 50, 51. So the answer is 51. So this is 51. That's it. This is the answer. So the main idea here is that we cannot find the result by expanding it. We cannot do that. Then we have to start finding the smaller values, then we can get this one. So that's all in this question. Now, one more question is there. So let us look at the next question in quiz 1. Now, let us look at next question in quiz 1. See, this is the program given, this is a function, and it is called for value 3. If you read this, the variables are n and d. Only two variables are there. But d is static. So you remember, when you have any static variable, you should take it separately. So let us put it as 1. Now, what is there inside? Just printfs are there. So, okay, it's easy. Let us do it. So, let us make a first call. C of 3. Instead of count, I am saying just C. Okay. So, C of 3, count of 3. Static, D is 1. Yes, this is over. This is initial, right? We don't have to repeat it every time. Print N. So, what is N? 3. So, print 3. Okay, here I will write on the output what we get. So, first time 3 is printed. Then, print D. What is a D? It is printed now, right? So D value, what is that? 1. So 1 is printed. So 1 is printed. Then D++. D++. D becomes 2. If n is greater than 1, then count n minus 1. So yes, it is greater than 1. It is 3. So count is called again for n minus 1. So it is for 2. The next print. But first of all, call is there. Finish that call and then print. Okay, printing will be done, but not now, afterwards. Then call for 2. Continue from here. Again calls itself. So again printing is there. So first print n. N is how much? 2. So 2. Next print d. D is how much? 2. So 2. Then D++. D becomes 3. N is greater than 1? Yes. Call itself for n minus 1. So C is called for n minus 1. 2 minus 1, 1. Then after that printing is there, but not now. It will be done afterwards. See, here also we left it. We have to do it afterwards. This time C is 1. Come again. Right? Print N. N is what? 1. Print 1. Then print D. D is how much? 3. So print 3. Then D++. So this is okay, 1 is printed and 3 is printed. Then D++. So D++, D becomes how much? 4. Then n is greater than 1? No, it's not greater than 1. So it doesn't call. So calling is not done. But after that, printing is there. So printing is done. So what is a D? 4. So now this is the end point, right? It's going to print now. So it is 4. 4 is printed. There is no call further. Go back. So it goes back to the previous call. So for this call, this is completed. Next is there remaining. Print. This is print. Print what? D. What is D? 4. So 4 is printed now. Then this call finishes. It goes back in this line, right? This one for this call. It is in this call now. This is over. Next is remaining. What is that? Print. Print what? D. D is how much? 4. So 4 is printed. So this is 4. So the answer is 3 1 2 2 1 3 4 4 4 is the answer. So that's all. This is the tracing and explanation of all quiz questions, right? So you can write this program and test them also. You get the same result. So that's all with quiz 1 problems.